In the fourth example, we are looking at the series from 2 to infinity. We're starting at 2 to make sure that the log at the bottom is not 0, of x minus 1 to the n divided by natural log of n. So this is a power series centered at 1, where the nth coefficient is simply 1 over ln of n. We're going to use the ratio test again, with the usual convention that an is a general term. And so we get, in absolute value, x minus 1 to the n plus 1 divided by ln of n plus 1 for the absolute value of an plus 1. For the reciprocal of the absolute value of an, we get natural log of n divided by absolute value of x minus 1 to the n. X minus 1 to the n plus 1 divided by x minus 1 to the n is just x minus 1. And then we have this quotient of logs. So what we want to know about this ratio is its limit as n goes to infinity. And to know that, we need to know the limit of natural log of n divided by natural log of n plus 1. And both top and bottom go to infinity, but we can look at the limit as x goes to infinity and use the rule of de L'Hopital. The derivative of ln of x is 1 over x, derivative of ln of x plus 1 is 1 over x plus 1. So we end up with a limit of x plus 1 over x, which is 1. So since the coefficient in front of absolute value of x minus 1 in the expression for our ratio an plus 1 over an goes to 1, that means that the limit of our ratio is simply absolute value of x minus 1, in other words, the distance between x and 1. And by the ratio test, we can conclude that our series is absolutely convergent whenever this distance between x and 1 is less than 1, and divergent whenever it is greater than 1. In other words, we have, for the interval of convergence, an interval centered at 1 of radius 1, so it's going to extend from 0 to 2, and we need to test these two endpoints, x equals 0 and x equals 2, separately. For x equals 2, if I plug x equals 2 in this expression, I get 1 to the n at the top, which is just 1, so we end up with a series from 2 to infinity of 1 over ln of n. And we want to know whether this series is convergent or divergent. A typical argument, something that you should keep in mind, is that ln of n goes to infinity, but it goes to infinity slowly. In particular, it goes to infinity slower than n. And so the reciprocal goes to 0, but goes to 0 slowly. And in other words, we should expect this series to converge, to have a behavior that is worse in terms of convergence than series of 1 over n. So more formally, I claim that ln of n is less than or equal to n for n greater or equal to 1. And let's assume for a moment that we know that this is true, and I'm going to justify it in a second. Then the reciprocal, 1 over natural log of n, is greater than 1 over n. But we know that the series of 1 over n is a divergent p series, right? For p equal 1, and whenever p is less than or equal to 1, the p series is divergent. So by comparison, we can conclude that our series of 1 over natural log of n is divergent. Now let's look at this claim again. Where does that come from? How can I justify this? Well, I'm just going to check that the function f of x, which is natural log of x minus x, is negative for x at least 1. And that's easy to see because the derivative is 1 over x minus 1. If x is greater than 1, then 1 over x is less than 1, so when I subtract 1, I get something negative. So for x greater than 1, the function is decreasing. And the value at 1 is already negative. It's ln of 1, which is 0, minus 1, so it takes a negative value at 1 and then it is decreasing. Therefore, the function is negative when x is greater or equal to 1. And that means that in particular, ln of n minus n is negative, which is another way of saying ln of n is less than or equal to n. Now looking at the other endpoint at x equals 0, if I plug x equals 0, I get negative 1 to the n divided by ln of n for the general term. And therefore what I obtain is an alternating series. And the sequence of absolute values is 1 over ln of n, which is decreasing with limit 0, and therefore by the alternating series test, the series is convergent. So we have this interval from 0 to 2, where the series is convergent at 0, divergent at 2, and therefore the interval of convergence is the interval 0, 2, where we include 0 and exclude 2. For the fifth exercise, we have the series from 1 to infinity of -1 to the n, x plus 2 to the n divided by n times 2 to the n. So this is a power series centered at -2, where the nth coefficient is -1 to the n divided by n 2 to the n. Using the ratio test as usual, when we take the absolute value of the ratio of two consecutive terms, we don't have to worry about the -1 to the n because of the absolute values, and therefore what we obtain for the absolute value of an plus 1 is x plus 2 to the n plus 1 in absolute value divided by n plus 1 times 2 to the n plus 1. The reciprocal of the absolute value of an is n 2 to the n divided by absolute value of x plus 2 to the n. So we have various things that cancel out here. We have 2 to the n at the top, 2 to the n plus 1 at the bottom. We can simplify 2 to the n. What remains is 2 at the bottom, so we have 1/2. Then we have n over n plus 1, and then x plus 2 to the n plus 1 divided by x plus 2 to the n is simply absolute value of x plus 2 at the top. And now we are looking at the limit of this quantity when n goes to infinity. When n goes to infinity, n over n plus 1 goes to 1. Therefore, the limit of our ratio is absolute value of x plus 2 over 2. And we can conclude by the ratio test that the series is absolutely convergent whenever this limit, absolute value of x plus 2 over 2, is less than 1, which we can write as absolute value of x plus 2 less than 2. And it is divergent whenever this limit is greater than 1, which we can write as absolute value of x plus 2 is greater than 2. So it's convergent when the distance to -2 is less than 2 and divergent otherwise. In other words, the interval of convergence is going to be an interval centered at -2 of radius 2. And that means that it's going to be the interval that extends from -4 to 0, and we need to check these endpoints separately. So at x equals 0 and x equals -4, let's take a look. At 0, if I plug x equals 0, I have -1 to the n, and then 0 plus 2, 2 to the n, divided by n 2 to the n. So the 2 to the n cancels out, and we end up with a series of -1 to the n over n, which is an alternating series where the sequence of absolute value of the terms, 1 over n, is decreasing with limit 0, and therefore the series is convergent by the alternating series test. On the other hand, for x equals -4, if I plug -4 in x plus 2 to the n, I get -2 to the n. But that's really just -1 to the n times 2 to the n. And -1 to the n multiplied by -1 to the n is -1 to the n squared, or -1 to the 2n, and that's just 1. The 2 to the n cancels out. We end up with just a series of 1 over n, which we know is a divergent p-series, for p equal 1. And therefore, we have found that our interval of convergence extends from -4 to 0, that the series is divergent at -4 and convergent at 0, and the interval of convergence is therefore the interval from -4 to 0, -4 excluded, 0 included. Finally, we're going to look at the series from 2 to infinity of x to the n divided by ln of n to the n. So far I always used the ratio test. Here I'm going to use a root test. Well, in the other cases we could have used a root test as well, but in this case it's particularly convenient because what we have is really the nth power of x over ln of n. That means that if I take the nth root of the absolute value of an, I have absolute value of x divided by ln of n. And what we want is a limit of this quantity. When n goes to infinity, natural log of n goes to infinity, and therefore our nth root of the absolute value of an goes to 0. And this is independent of x. In other words, the limit is less than 1 for all x, which means that the series is absolutely convergent for all x. In other words, the interval of convergence is the entire real line. Now turn to the next video for other remarks on the interval of convergence of a power series.